2.1, number 31. This is just kind of a thinking question here, guys. There's not a ton of work to do on this one, but let's see what we've got. So they give you a graph over here with two functions. That first one, we're going to get used to this a little bit later on in the semester right here, is what we call a function that is increasing at an increasing rate. That might be something like, and don't write this down, guys, but it might be something like y is equal to e to the x. Exponential growth functions increase at an increasing rate, whereas the second function is still increasing, but this one is losing steam as it moves from left to right. We would say that this is increasing at a decreasing rate, and an example of that might be something like a logarithmic function, y is equal to natural log of x. Now, none of that is really important right here. In fact, I'm going to undo everything I just wrote, and let's try to actually answer the question. Which graph in this figure has the following property? All right, for all x values in your domain, the average rate of change on the interval from 0 to x is greater than the instantaneous rate of change at x. And we're supposed to explain. So what I'm going to do here is choose just a random point, and I wish they hadn't used x, because that sounds like it's just a variable. I wish they'd done something like c, but same basic idea. Let me put a c right here, and I'll try to put a c in roughly the same spot. They want us to compare, in each one of these graphs now, the average rate of change of these functions on the interval from 0 to what I'm going to call c. They were calling x. So here's where we are when x is equal to 0, and here's where we are when x is equal to c. And an average rate of change is the same as the slope of your secant line. So that's what the secant line in graph A is going to look like. And in graph B, it's going to be pretty similar, guys. Here we are at x equals 0. Here we are at x equals c. 2 points right there, so I will define that secant line as passing through those. And each one of those green lines has a slope. Now their slopes relative to one another, kind of irrelevant. What they want us to do though is compare that to the instantaneous rate of change at x, or what I'm calling c. So now what I'm going to do is I'm going to switch to blue here. And here's the main important thing I want to make sure that we get down, guys, that an average rate of change is equivalent to the slope of your secant line. That's why I drew secants there in green. But when we start talking about an instantaneous rate of change, now we're talking about the slope of a tangent line. So what I'm going to do is go back to this first graph right here, and at the spot where x is equal to c, now I'm going to attempt to draw the tangent line passing through that point there in blue. And I'm going to do the same thing in the second graph. Here we are at c, but now this tangent line is going to look something like that. Now there's a big fundamental difference here between graph A and graph B, and here we go. At point C right here, the tangent line that we have drawn at point C is steeper than the secant line was. But in the second graph, the tangent line that we drew is less steep. So the question was, okay, in which of these graphs has this property here where the average rate of change on the interval from 0 to c is greater than the instantaneous rate of change at c? We want to know, where is the slope of the secant greater than the slope of the tangent? Does that happen on graph A, or does that happen on graph B? It's graph B here, guys, where the slope of the secant is greater than the slope of the tangent. And that would have happened at any c value that I had picked along the way. Whereas in part A, the function that was increasing at an increasing rate, that tangent line is always going to be steeper than the slope of the secant. So our answer right here would be graph B.